Okay, here we're going to talk about something called the change of base formula. I'm not a big proponent of using the change of base. I kind of like the algebraic methods, so I'm going to have you do both though, because the algebraic methods will be used in the next section when we solve for logarithms and exponentials, so it's nice to know it. So anyway, this is how we get the change of base. We're going to look at evaluating log base 3 of 12. Alright, some calculators now can actually do that, but most calculators only have base 10 and base e, natural log. So what I usually do is I say, okay, I don't know what this is, so I set it equal to an unknown, say y. And then we change it to an exponential, meaning this is log form, so I change it to the exponential. 3 to the y equals 12, right? So let's write that. 3 to the y equals 12. That's changed to the exponential. So if you're in log form and you can't solve it, change it to exponential form. Okay, 3 to the y. Now to take the log of both sides. So just like I can add 5 to both sides, I can divide by any number I want on both sides. I'm going to actually take the log and I'm going to choose a base 10. Okay, log base 10 of 3 to the y equals log base 10 of 12. Why do I choose base 10? Because the calculator can evaluate that. Alright, then we're going to use power rule, because there's this exponent, right? I'm trying to solve for that exponent. I'm going to bring it down out front. Now it's y times log base 10 of 3 equals log base 10 of 12. Now what do you suppose I'm going to do next if I'm solving for y? Right? What do you think I'm going to do? Yeah, I'm going to divide both sides by log base 10 of 3 right here, this guy. Get rid of this function so that it says y equals, right? So I divide both sides by that like this, log base 10 of 3, log base 10 of 3, and I get y equals log base 10 of 12 over log base 10 of 3. Now don't reduce these. 12 divided by 3 is not what this is saying. You might want to put parentheses around there. Remember, this is the input to the log function. This is the input to this log function. It is a log divided by another log. You must evaluate this and then do the division. Okay? So how do we get that? We use our calculator. So let's switch over to the calculator here. Now we take the log. Here's our log key. So we say log 12. See, it has to be like that. You close the parenthesis, and then you can do divided by log 3. Close the parenthesis. That's what that says exactly, right? And you get 2.26. Now, if you did it differently, like log 12, and then you did divided by 3 like this, that's really the log of 4. And that's a different number. See, look at that. That's really just this, the log of 4. And that's not what it is. It's the log of 12 divided by the log of 3. You got to make sure you do 2 logs there. So what do we have? 2.26 about, right? So this is about 2.26. Okay, that's your approximation to that. But now let's look here. Notice that the solution to this is the log of 12 over the log of 3. And then we have base 10. It's called the change of base. But look at the number. Look at what it was. It was log base 3 of 12. So it was log of what you're wanting to take over log of the base. So log base 10 of 12 divided by log base 10 of 3. So that's the formula basically. So if you have a change of base formula, it looks like this. If you take the log base b of x, you take the log of x over whatever base you choose, and normally we choose base 10 because our calculator has it, and then we choose log base 10 of the whatever this base is, b. Now you could choose the natural log. What was our number again? Let's just show you that. It's log base 3 of 12. So log base 3 of 12. Okay, we know our answer. So watch this. I could do, okay, the natural log. Let's go natural log because I'm going to choose base e. The natural log of the top one over the natural log of the whatever the base is 3. Now this is a ratio, just like the other's a ratio. This will give me the same answer. let me pull up the calculator and watch this. Natural log of 12 divided by the natural log of 3. Because I can choose any base and do this, this ratio will come out to be the same as this one, 2.26. There it is, 2.26, same thing. So this equals 2.26. So we can choose any base we want. The reason why I choose base 10 or base E is because the calculator uses it. Let's try a couple more. I'm going to do these out by algebra and then quickly solve them with a change of base. I like the algebra approach. I'd like you to try the next couple with algebra. So algebra, how do I evaluate this? Set it equal to an unknown, change to exponential, 4 to the y equals e, 4 to the y equals e. Now I'm going to take the log of both sides because I got to get this guy down, right? So if I log both sides, I could choose base 10, which is totally fine, but I have an e in here, right? If I have an e, why don't I just choose the natural log like that? That's base e of 4 to the y. The reason being is because what happens here? What's the natural log of e? Yeah, that's just going to be 1. So that just makes things a little easier. Next step, use the power rule, bring the 4 or y out front. So it's y times the natural log of 4 equals, again, we just got done saying, that's going to be 1. Then I divide by natural log of 4. Divide by the natural log of 4, divide by the natural log of 4. So the exact answer is this. So if I ever ask you for an exact answer, that's the exact, right? Now if I ask you for the approximate, pull up the calculator, go ahead and put the approximate answer in by taking, it says it's easier to see to do this. See, 1 divided by the natural log of 4. The natural log of 4. That's just a little bit easier to put that information in. 0.72. Okay? So, and that's approximately equal to 0.72. Approximate, exact. Okay? Try this one. Oh, let's quickly go back to here actually and show that the change of base, if I erase all this mess here, if I just did the change of base formula, I would get the same exact information. Log e, but let's take the natural log of e over the natural log of 4. But the natural log of e is 1, and there we go. Same thing, right? Super easy, but it's kind of like a trick, right? And what this does, this process right here, actually helps you solve logarithms because it's going to happen the next time. So let's do this again. Let's make this equal to x this time. Again, 9 to the x equals the 31, right? Log both sides, base 10 this time, because there's no, I could use natural log, I'm just using base 10. Power rule. Divide both sides by log 9. So we have log base 10 of 31 over log base 10 of 9. Again, same thing, use the rule, right? It would have been log 31 over log 9. What does that equal to? Log 31 divided by log 9. 1.56. Exact, or approximate, exact. Alright, let's have you try one here. See if you can work it by algebra and then also work it out with the change of base formula. Okay, give your pause it and see if you can do either of those, or hopefully both. Okay, algebraic approach is I set it equal to some unknown and I change it to exponential. 2 to the power of x equals the 5, right? 2 to the power of x equals 5. I take the log of both sides. I'm going to choose base 10. Log base 10 of 2 to the x equals log base 10 of 5. Power rule. X times log base 10 of 2, log base 10 of 5. Divide both sides by log base 10 of 2. And I have x equals the log base 10 of 5 divided by the log base 10 of 2. And that's exactly the same thing I would have if I did I did the change of base formula, I have the log of what we're taking the log of, right? Log of 5, base 10 I choose, over the log of the base, over the log of 2. So what's that approximately equal to? Check on the calculator. Log base 2. Or sorry, log base 10 of 2. Hit enter. 2.32. Remember, the 2.32 is actually what this is equal to, right? Or approximately equal to. 2.32. They're the same thing. Okay?